This works, I know.
No, slide change.
That we have checked.
Okay, so welcome back after tea coffee break. So we have Professor Jagadheep Pandian, so who will be teaching you more technical stuff, related to what you are more familiar with. Okay, so he will be teaching Fourier transform and its application, and also associated topics with that. So Jagadheep, welcome.
Okay, thank you, Naren. So before I start, I would just like to get a quick hands up on how many of you are engineers and have done a course on signals and systems. Okay, just a handful. Okay, but how many of you in general are familiar with the idea of Fourier series, Fourier transforms? Okay, most of you. Okay, that's very good. All right. So today what I am going to do is speak from an engineer's perspective, not from a scientist's perspective, on introduction to Fourier transforms. So I will cover a set of topics. So Fourier series, we'll start off with Fourier series and periodic signals. Then what about Fourier transforms? So they are related to aperiodic signals, not periodic signals. Then properties of the Fourier transforms. Then we'll talk about a sampling theorem, that's a Nyquist theorem. And this directly leads to a discrete Fourier transform. Okay, so let's start off with the Fourier series. So this, just a very quick historical perspective. So this is named after a person called Fourier. So Jean Fourier, who proposed in 1807 that any periodic function could be represented by a weighted sum of different frequencies. Okay, so it was just a proposal at that time. And 4 distinguished mathematicians were appointed to examine this paper, and out of that, some were in favor and some was vehemently opposed. You can see many of these are very famous personalities. And finally, this paper was actually never published. Okay, so that original idea was never published. So finally, Fourier published this in a book, and this is what finally became a Fourier series. Okay, so what is a Fourier series? So let's assume that you have a periodic signal, which means that your x of t is same as x of t plus capital T, where capital T is a period. So then what Fourier said is x of t can be represented by infinite sum of a large number of complex exponentials. So of course complex exponential means you have sine functions and cosine functions. So this coefficient, so remember I said it's a weighted sum. So these coefficients are related to the signal, and this omega naught of course is just 1 over capital T. And coefficients are given by 1 over t into integral over 1 period x of t into e power minus ik omega naught t. So this is just the definition of Fourier series. So now the question is, can any periodic signal be written as a Fourier series? What do you think? Yes or no? So as long as I satisfy this condition, can anything be represented as a Fourier series? How many think yes? That means none of you think it as yes. So can I assume all of you say it's no? How many say no? Okay. What about the rest of you? Neither yes nor no means what? Yeah, see, I would like this to be an interactive, okay? It's not meant to be a very formal thing where I'm teaching and... Okay, so it has to satisfy some conditions known as Dirichlet conditions. Okay, that is a condition you need in order to represent a signal as a Fourier series. First thing is, should be absolutely integrable. That means that the sum over a period of x of t must be less than infinity. The second thing is that in any finite interval of time, the number of maxima and minima must be finite. And also, there should be a finite number of discontinuities. So I'll give you some examples of signals which do not satisfy these two conditions, and so those are signals for which we cannot represent them as a Fourier series. So this is an example of a signal. For example, if you look at something like sine of 1 over x, so that will have a signal whose frequency is continuously changing. And so this has an infinite number of maxima and minima, so it does not satisfy the first Dirichlet condition. This is an example where within one period you have a huge, almost infinite number of discontinuities. So again, it does not satisfy one of the Dirichlet conditions. So these are the kind of signals which cannot be represented as a Fourier series. But normally, of course, we do not encounter these sort of signals in practice. So normally we have impulse signals. So just as an example, it's a square wave of period t. So if you have a square wave, so this is a square wave. So you can calculate what are the coefficients, Fourier coefficients, and you can keep on adding more and more number of terms in our summation. And you can see as the number of terms increases larger and larger, you get a more accurate representation of the square wave. Now in relation to this, you should point out that if you look at the edges, so there will be some deviation between the actual signal and the representation by your sum of cosines and sines. And this has to do with the fact that sines and cosines are continuous signals. And so you cannot really represent a discontinuity perfectly by just using a set of continuous signals. Okay, so this leads to a phenomenon which we call as Gibbs phenomenon. So again, when you actually do some actual data processing, you will encounter this phenomenon, and there are techniques which people come up with to minimize this phenomenon. So here what we observe is that when a signal experiences a discontinuity in its amplitude or its slope, the reconstructed signal will deviate. You cannot have a perfect reconstruction. So for example, this is the same square wave where I showed you that towards the edges you get almost a 9% discontinuity. And even if you increase the number of terms in your Fourier series to a very large number, this remains the case. Okay, so that's what we call as Gibbs phenomenon. And the way it manifests itself in actual radio signal processing is when you have a very sharp signal, like for example a spectral line, which is a very narrow signal, and you want to try to observe that signal with a radio receiver, sometimes you will find this sort of ringing where you have these oscillations, which is not real, it is not inherent to the signal coming from the sky, it is an artifact from our processing that we have in our signal. Okay, so this is about a Fourier series, and now let's look at aperiodic signals. So if you look at an aperiodic signal, you can consider as a periodic signal whose period tends to infinity. So if you just consider one period of a periodic signal, what happens to the Fourier series as the periodicity is increased? Okay, so let's take a look at our again simple square wave, and you, let's say capital T is just some arbitrary units, let's pick it to be 2, and now what I'm going to do is I'm just going to increase its period. So you can see what happens. So this is period of 4, period of 16. So what you can see is the overall envelope, it remains the same. Okay, all that happens is your Fourier coefficients become closer and closer spaced. Because remember the Fourier frequency is related to 1 over period. So when period becomes very, very large, the frequencies, that is the separation between the different Fourier series coefficients becomes very, very small. Okay, so in essence, when capital T tends to infinity, you just get a continuous signal here. And that is what the Fourier transform leads to. Okay, so as the period increases, the Fourier components are getting closer and closer together. And so the envelope of the Fourier components remains the same. So in the limit of capital T tending to infinity, so this just becomes the Fourier transform. So as capital T tends to infinity, so you can just say x of omega, instead of having a summation, you just put it as an integral because your frequencies become infinitely closely spaced. So you have an integral minus infinity to infinity x of t to the power minus I omega t dt. So the only difference between the engineers and us astronomers is engineers like to use omega and astronomers tend to use frequency nu. So you just write omega as 2 pi nu. That's the only difference. Okay, so a similar equation actually applies to spatial frequency, except that instead of time frequency, your spatial frequency k is 2 pi by omega, which is replacing your temporal frequency, which is 2 pi divided by capital T. So this is an example of low spatial frequency and high spatial frequency. So when Mayuresh talked about interferometry, so this is exactly the same phenomena, where you have different telescopes spaced at different locations, and so you have fringes on space. Okay, so those fringes are related to the spacing between these two telescopes. So those are what we call a spatial frequency. Whereas temporal frequency is something signals which repeat as a function of time, like the pulsar signals that he showed you the first lecture. So let's consider again the simple rectangular function. So you have x of t as a function of t, where you just have the signal going from minus half to plus half. So then you can calculate the frequency. So I'll just switch to new, because this is what we usually radio astronomers use. So you just do the simple integrals. Of course, the signal is 0 for all of the time. So your integral minus infinity to infinity just becomes from minus half to plus half e to the power minus I 2 pi nu t. And so this gives you a simple sin x by x type function, which is defined as a sinc function. Okay, so this is sinc of nu. So if you plot sinc of nu, this is what it looks like. And this is a signal which I showed you as example for how you go from the Fourier series to a Fourier transform. Okay, I'll just show you some other examples. So this is a simple exponential decay. So if you have x of t is 0 for t less than 0 and is e to the power minus at for t greater than or equal to 0. So again, you can calculate the Fourier transform, so a very simple integral. And so what you will get is x of nu is 1 over a plus I 2 pi nu, which if you calculate what is its magnitude, so mod of x of nu whole square, so you will just get this function which we call as a Lorentzian profile. Okay, so some of you have been doing some spectral line observations, you will be familiar with the Lorentzian profile. It has to do with quantum mechanics, which is a completely different aspect come from what we are talking about here. So this is what the Lorentzian profile looks like. So these are different signals for different values of A. So when A is large, so it becomes a very steep function. When A is small, it becomes a shallow function. So with a shallow in time, you get a very steep Fourier response, and when it is very steep in time domain, you get a very shallow Fourier response. So always there is a rule of thumb that whatever your response is in time domain and frequency domain, they are almost like an inverse relation. That's because frequency and time are almost inversely related to each other. Okay, another example, Gaussian. So if you calculate x of t is e to the power minus pi t square, so it turns out that your Fourier transform is another Gaussian. So as I said, only relation is in terms of how steep the signal is in time domain versus frequency domain. And this is a special case where for e power minus pi t square, you get exactly the same function in the Fourier domain. So Fourier transform for Gaussian is just another Gaussian. So now let's look at some properties of Fourier transforms. So this is what usually we use to come up with more complicated examples for Fourier transforms. So if I have simple signals which are linear sums, so if I have x of t's Fourier transform is x of mu, and y of t's Fourier transform is y of mu. So then you have a linear sum a into x of t plus b into y of t. The Fourier transform is simply a into x of mu plus b into y of mu. It's fairly straightforward. Then if you shift it with time, so if you say x is, if I have x of t and I construct a delayed version of that same signal, x of t minus t naught, so what happens is you can put t minus t naught as a new variable t prime and calculate that integral. So you will get exactly the same Fourier transform but with an extra phase term. Okay, so this again you will see how it applies when you do interferometry, because if I have a signal exactly in the center of my array, I will get one signal. If I have the same source which is slightly offset, I will get exactly the same signal but with a phase term, because it's exactly what is happening is shifting in time or shifting with respect to space. Okay, so you just get x of nu multiplied by e to the power minus I 2 pi nu t naught. So the amplitude stays the same, but the phase shows a shift that is proportional to the frequency. Now if you look at complex conjugate, so just take complex conjugates, e to the power I 2 pi nu just becomes e to the power minus I 2 pi nu. So what happens is you will get x star of minus nu. So if x of t's Fourier transform is capital X of nu, the Fourier transform of the complex conjugate is the same signal but whose complex conjugate you have to take and also replace nu with minus nu. So again, these are very quickly you can construct the proof by just looking at the expression for the Fourier transform. So if I have a real signal, that means the signal and its complex conjugate are one and the same, which means that you have some symmetry properties for the Fourier transform itself. So therefore, if x of t is real and even, what you will also have is a Fourier transform is also real and even. And if x of t is real and odd, what will happen is your Fourier transform will be imaginary and it will be odd. So again, I'll show you some examples later on when you think at cosine signal, which is a real signal which is also even, and a sine signal which is as real but it is odd. Okay. Another property of Fourier transform, again highlighting the inverse relation, is if I construct a signal which is x of at, I will get a Fourier transform which is capital X of nu by a, and you also have a scale factor. Okay, so again, if you just look at time reversal, so convert t to minus t, all that happens is nu becomes minus nu. So again, to showcase this example, so if I construct a linear signal whose which exists for a very short amount of time, you will get a sinc function here. If I now scale it, make the signal larger, what will happen is the Fourier transform domain will become correspondingly narrower. Okay, so this to this is just 1 over this to this, that's it. Also, if I have x of t whose Fourier transform is capital X of nu, then if I construct a signal in time domain which is the same function as a Fourier transform, its Fourier transform will be similar to the signal which I had in the time domain. So to give an example, so remember I had a rectangular function and I said its Fourier transform is your sinc function. So suppose I construct a time domain signal which is sinc function, its Fourier transform must be a rectangular function. Only thing that happens is your time coordinate and frequency coordinate, you have a minus nu term here. Now, some more interesting properties, that is with respect to area. So this comes about from your formulation of the Fourier transform, where you just put capital nu or nu to be 0, then what you will get is integral minus infinity to infinity x of t is capital X of 0. Okay, so I'll give you an example of how this manifests itself. So if you think about an interferometer, so it means you are just looking at signals, how they correlate between two different telescopes. You cannot put two telescopes on top of each other, which means that you simply lose the total power information. So therefore, if I look at the total sum of all the amplitudes that I get in the interferometer, they will average out to 0. Okay, and it's only by using other techniques, like you will learn about it in next week, something known as cleaning, that we will recover some finite amplitude. Otherwise, total amplitude will work out to be 0. Okay, and same way, x of 0 is integral minus infinity to infinity capital X of nu d nu. Then we have, of course, the famous Parseval's theorem, which you may be familiar with, that if I look at the square of the signal's amplitude in the time domain and look at the square of the amplitude of the Fourier transform in the frequency domain, they are one and the same. Okay, so this equality is what we call as Parseval's theorem. So just to summarize what we have learned so far, so this is the relation for the Fourier transform and this is the relation for the inverse Fourier transform. Okay, so you just have replace e to the power minus I 2 pi nu t with e to the power plus I 2 pi nu t, you get inverse Fourier transforms. Okay, now in order to move forward, we need to also learn something about a signal known as Dirac delta function. Again, I think many of you will be familiar with it. So the Dirac delta function is a function whose amplitude is 0 everywhere except for t equal to 0. And at time t equal to 0, the amplitude is actually infinitely large. So its amplitude is not well defined, but it's defined in such a way that the area under the function is unity, which means delta of t is 0 for t not equal to 0, but the integral from minus infinity to infinity of delta t is equal to 1. So you cannot define a delta function for a time t equal to 0. That is not well defined, but the area is 1. So if I have a signal x of t and I just integrate this x of t with a delayed version of that delta time, so what you will see is this delta function is 0 for all t not equal to t naught, and the area of the delta function, when you just cover a small interval around t naught, it will be equal to 1. So therefore, it will just pick up the value of the signal at x equal to t naught, because the signal vanishes for all time t not equal to t naught. Okay, so this is how you pick values of the signal. So this is important when we come to how you sample the signal in terms of time domain or frequency domain. So delta functions are very, very important. Okay, so it follows the delta of t as a Fourier transform of 1, because if I remember the definition of delta function, its amplitude is 0 for t not equal to 0. So if I just look at integral of delta t e to the power minus I 2 pi nu t, so that vanishes everywhere except for t equal to 0, and at t equal to 0, e to the power minus I 2 pi nu t is 1. Okay, so the amplitude of this delta function is just 1 everywhere. It's constant amplitude for all frequencies. So now if I look at this
Okay, so this has exactly the same amplitude of 1, but if you look at the phase of the signal, that is linear with respect to nu. And the same way, remember I talked about the duality. So if x of t has capital X of nu, then capital X of t will have small x of minus nu. So if I just look at, instead of, I just put this function and I replace nu with nu naught. So what you will have is delta of nu minus nu naught. So given that this is the basis for sines and cosines, so I can now tell you what are the transformations for sine signals and cosine signals. So cos 2 pi mu naught t is e to the power I 2 pi mu naught t plus e to the power minus I 2 pi naught t divided by 2. So therefore its Fourier transform will be half into delta of nu minus nu naught plus half into delta of nu plus nu naught. So if you look at it in terms of Fourier space, you have one delta function at plus nu naught, one delta function at minus nu naught. Again showing that the Fourier transform is real and it is also even. If I look at sine, so sine is e to the power I 2 pi nu t naught minus e to the power minus I 2 pi nu t naught divided by 2i. So therefore its Fourier transform will be 1 over 2i into delta of nu minus nu naught minus delta of nu plus nu naught. So now you have a delta function at nu equal to nu naught and another delta function nu equal to minus nu naught, but with an amplitude of negative, and the amplitude is 1 over 2i. So therefore again you can see that the Fourier transform is fully imaginary and it is also odd. Okay, so the amplitude in the minus frequency is minus of the amplitude in the positive frequencies. So to give you a preview of what you are going to learn next week, so in interferometry what we are doing is we are taking the outputs from different radio telescopes and you are going to do cross correlations. So what this will create is essentially like a Young's double slit experiment where each pair of telescopes is going to create a fringe pattern whose frequency is 1 over the separation of these two telescopes. And what you will see is that these cross correlation products are what we call as visibilities, and the actual image in the sky, like what Mayuresh showed, for example, that image of the pulsar which he was able to detect for RRAT. So that's an image from interferometer. Okay, so that image and your visibilities are a Fourier transform pair. So whatever we have learned about Fourier transforms, if you will understand that properly, you can just look at the visibilities and sort of get a very good idea of what the image will look like. So by examining the visibilities, you can deduce some basic properties of the source. So just as an example, if I have a point source like what Mayuresh detected for a neutron star, what you will see for the visibility is constant amplitudes. Which means if I plot the visibility as a function of the spacing between the two antennas, which are, and you will learn why it is called u comma v, that you will learn next week. Okay, but if I plot it as a function of spacing between the antennas, you will see that visibilities are a constant, which immediately implies that the Fourier transform is a delta function. Okay. If I have a Gaussian like shape like this, then remember I said that the Fourier transform of a Gaussian is another Gaussian, but the width in the frequency domain is 1 over the width in the time domain. So here I have a small width in this domain, so therefore you have a large width in this direction, a large width in this direction, so very small width in this direction. Okay, so if you see a Gaussian shape like this, you can infer that the sources will be another Gaussian like that. If I have a disk, so that is essentially a rectangular function but in two-dimensional space. So again you will have something analogous to your sinc function, but in terms of 2D circular aperture you will get what is called an Airy function, which is a Bessel function. So this is what you will see. Okay, so we'll give a Bessel function here. And the same way, if I have multiple rectangles at different locations, again the amplitude will be similar to this, but remember I said the phase will have different components depending on how far away these disks are from the central location. So that's why you get a total signal which looks like this. So this is just to again showcase that if I have a narrow signal in the XY plane, you will have a broad signal in the UV plane. But if the signal is now centered in the origin, your phase will be 0. But now if I take exactly the same signal and slightly offset it, what you will see is a linear phase. Okay, so again if you look at the signals in your interferometer and you look at the behavior in terms of amplitude and phase, you can get a very good idea of what kind of signal you're looking at and what is the location of that signal. Okay, so with that aside, we'll go to a slightly different topic, and that is about sampling and the Nyquist theorem. Okay, so what is sampling really? Anyone? Okay, close but not exactly. So literally, yeah, you want to say? Yeah, so that means what does it do? So it just picks, okay, it just picks the values of the signal at discrete intervals of time. So instead of a width, actually literally it is a delta function. So it's not a finite width, it is as close to delta function as possible. Okay, so it is essentially just picking out values of a signal at regularly spaced intervals of time. That is what sampling really is. So mathematically it is equivalent to exactly what we had heard, that it is multiplication of a signal with an infinite impulse train. Okay, so if you have x of t, then your sampled version is what we have put here as xp of t, that is just multiplication of x of t with a sampling function, where the sampling function is just an infinite impulse train, delta of t minus n times capital T. So again, to showcase what it is doing, so this is your x of t, this is your sampling function, so you have infinite number of delta functions here, and so what you are going to get is the values of x of t at the locations of these impulse functions. So you will get a value of the function here, value of the function here, value of the function here, etc. So this is your sampled version. So now the question is, given my sampled version, so if I just give you these data points, can you reconstruct the original signal? Pardon? Depends on the sampling frequency, very good. So the answer is yes, under certain conditions. So it depends upon, like what he said, what's the sampling frequency. So let us see why you can do this and how this comes about. So let us assume that this signal x of t is band limited, which means that it has some maximum frequency nu. Okay, so this is my simple cartoon of my Fourier transform of x of t. And the shape doesn't matter. What matters is that it has a well-defined maximum bandwidth. So now if you look at the sampling frequency, sampling signal, which is the infinite train of delta functions, you can recognize that this is an example of a periodic signal. Now if it is a periodic signal, I can write it in terms of a Fourier series, right? So exactly the first part of what I have talked about today. So you calculate what are the Fourier coefficients by using the same formula as what I have told you in the beginning. So 1 over capital T integral over one period, so minus t by 2 to t by 2. So from minus t by 2 to t by 2, there is only one delta function, that's at time t equal to 0. Delta of t e to the power minus I 2 pi kt by t dt. So therefore it just picks out the value of this signal at time t equal to 0, because this delta function is 0 for all t not equal to 0. So therefore you just get 1 over capital T, because this term at t equal to 0 just becomes 1. So therefore your P of t is equal to 1 over capital T summation k equal to minus infinity to infinity e to the power I 2 pi kt by capital T. Now the Fourier transform of this is a delta function, right? Because remember I said that delta of t minus t naught gives e to the power minus I 2 pi nu t naught, or delta of nu minus nu naught gives you e to the power I k pi nu naught times t as its Fourier transform. So you can use this property to write down the Fourier transform of the sampling function. So that is 1 over capital T summation from k equal to minus infinite to infinite delta of nu minus k over t. So therefore what you will see is that the Fourier transform of your sampling function, which is the sum of an infinite number of delta functions, is another infinite train of delta functions, but whose separation is related to 1 over the sampling period. So your sampling period is capital T, here the separation between your delta functions in frequency domain is 1 over t. So here if this is t, this is 1 over t. Okay, so this is a Fourier transform pair. So if you have P of t of this, you will get P of Fourier transform P of nu to be this function. Now, Multiplication in time domain, it translates to a convolution in frequency domain. And I apologize because I don't have time to explain what's the meaning of a convolution. But essentially, what will happen when I convolve the delta function is, everywhere where there is a delta function, I will replace it with that function itself. Okay, so what will happen is that the Fourier transform of your sampled version of the signal corresponds to infinite copies of your transform, this individual signal. Okay, so what will happen is, remember I had just one period earlier. So wherever I have the delta function, I just replace it with this function itself. So essentially what is happening is, this I am replicating here where this separation is 1 over t. Okay, so that is what happens in the Fourier domain under convolution. Okay, and just to show, this is minus nu to nu, and so your 0 now becomes 0 plus 1 over t, so your minus nu m comes to here, minus nu m plus 1 over capital T. And so now what you can see is, as long as this frequency and this frequency, there is a separation between them, the copies of each repeated spectrum is preserved, so you don't have any modification of that. And so therefore you can see that if this condition is satisfied, you need a condition that 1 over t must be greater than twice the bandwidth, twice your maximum frequency. So 1 over t is a sampling frequency, that must be larger than twice nu m in order for this separation to be maintained. Okay, at the limit where 1 over t is exactly equal to 2m, this and this will touch. Okay. And that is what we call as a Nyquist theorem. So Nyquist theorem essentially states that if you want to sample a function and you want to be able to reconstruct the original signal from the sampled values which you have, you need to sample the signal at a frequency which is at least twice the bandwidth of the signal. Okay, if you sample it at a higher frequency, well and good, but if you sample at a lower frequency, then bad things are going to happen. And so what will happen? So if you need to reconstruct a signal, you just pass it through a low pass filter. So low pass filter means it passes all the signals below a certain maximum frequency. That's why it's called low pass filter. It passes all the low frequency, cuts off all the high frequencies. So when you do this, you will just again get the individual Fourier transform, and therefore you can immediately get back the original signal. What happens if this Nyquist theorem is not satisfied? So then we get something known as aliasing. Okay, so what happens is, so now your sampling frequency is lower, so this term will come only up to here when you copy it. So this is minus nu m plus 1 over t, this is your maximum frequency, and so these two terms will add. So what will happen is, you will just get a signal which looks like this. So the signal is completely corrupted, and there is no way for you to get back the original signal. But the interesting thing is, these are positive frequencies, these are negative frequencies, but these are also very high frequencies. These high frequencies appear to come at a lower frequency. Okay, so that is what we call as aliasing, where a high frequency component appears to come from a lower frequency component. So some high frequency component of x of t gets aliased to lower frequencies. And this is something which I am sure all of you observed in your day-to-day life. You may not have connected it to Nyquist theorem. So for example, suppose you are observing how a fan rotates, ceiling fan or a table fan or something, your eye is also sampling the signal. It is not continuously sending signals to the brain. It is continuously sampling the signal. So if your fan's rotation speed is such that your eye is sampling at a lower rate, sometimes what you will even see is the fan appears to rotate in the opposite direction. I'm sure all of you would have seen it, right? Or the fan appears to rotate at a very slow frequency, not the true frequency. That is because your sampling frequency is going to violate the Nyquist condition. Okay, so due to the sub-Nyquist sampling rate of the eye, the fan appears to spin at a very slow rate or even opposite, backwards. So this is just an illustration of how this works. So you have a high frequency signal, you are sampling at sampling frequency lower than twice the frequency of the original signal. So if you reconstruct the signal, it appears to have a lower frequency here. And you also see it in images. So sometimes you would have taken images on your cell phone of a brick wall, okay, and you will sometimes see patterns like this. Okay, so this in the context of image processing is what we call as a MOIRE, M-O-I-R-E, and again this shows the effect of Nyquist sampling being violated, because what is happening is you are having a periodic signal in the spatial domain, and your pixel spacing must be smaller than twice the frequency in the spatial domain in order to recreate this signal properly. And if the number of pixels on your cell phone device is such that this is not Nyquist sampled, then it appears to show some frequency components which are larger than the true signal in the actual building. Okay, so that's what gives you these sort of patterns. Okay, now theoretically, as I have said, we can reconstruct the signal if it is sampled at exactly equal to the Nyquist rate. But in practice, what happens is this requires an ideal low-pass filter where you have infinitely sharp edges to the low-pass filter. And so such filters you cannot reproduce in practice. Usually filters have a finite edge. So ideally what you want to do is sample the signal at greater than the Nyquist sampling. So if you use an ideal low-pass filter, it equivalents to interpolating with a sinc function which requires ideally infinite number of samples to converge. So in practice, you will always do sampling at higher than the Nyquist rate, so that you can reconstruct the signal with normal, non-ideal response function. And usually what one will do in practice, so especially for example, in order for this signal, what I am speaking to be able to pass to these speakers, what is being done is my voice signal is being sampled here. That is converted to a sampled version. Then it is digitized. Then it is passed there, some processing happens, amplification, and then it is reconstructed. So in order to avoid this sort of aliasing effect, what normally one will do is one will pass it through a filter, what we call as an anti-aliasing filter, so that all signals which are greater than a certain signals are filtered out, so that you avoid this aliasing problem. Okay, so you artificially clip the signal to a maximum frequency, then you sample it. So in that way you will not have any loss of signal beyond what is cut off by the original anti-aliasing filter. Okay, so that completes my introduction about Nyquist theorem, and now we can come to what is this discrete Fourier transform. Okay, the reason why I come to this in this particular way is normally if you just simply look at the discrete Fourier transform as a mathematical function, you will not appreciate the rationale behind what it actually is. All right. So far we have looked at continuous signals and their Fourier transforms, and now in practice we know that all our measurements are finite. Okay, if you take measurements in space, they are also at discrete intervals of time. If you take measurements in frequency also, they are at discrete frequency intervals. All the measurements are discrete. So the signal processing in the frequency domain also deals with discrete quantities. So therefore we will look at the discrete Fourier transform and how it relates to your continuous Fourier transform that we have talked about. So let there be a signal which is limited in time. Okay, so the signal is non-zero only for time 0 less than t less than some t max. So just having some arbitrary signal here. And its Fourier transform is also such that the energy is negligible beyond some bandwidth. Okay, so again you are having some maximum bandwidth. So it may not go to exactly 0, but the value is so small that it is negligible. So now what we do is we sample this signal in the time domain at a sampling rate that is greater than 1/2b. So remember the total bandwidth here is 2b. So therefore according to the Nyquist theorem we want to sample the signal at a frequency which is greater than 2b. So we will sample this. What happens is signal becomes periodic in the Fourier domain. So now you have a sampled version of the signal, and this gives you this infinite sequence of signals in the Fourier domain. Is this clear? This is just the same thing that we talked about when I talked about the Nyquist sampling theorem. Now I will go one step further and say I am going to sample the Fourier transform with an infinite impulse train separated by mu naught. Okay, so that same Fourier transform which I had showed you earlier, now I am going to sample that. So now if I sample in the frequency domain, I am going to make it periodic in the time domain. Okay, exactly the same thing because of the duality principle that I had told you in the very beginning. So now therefore what will happen in the time domain? The signal becomes periodic with a frequency which is given by 1 over mu naught. So here one version of the signal I am just going to reproduce it infinite number of times with a separation given by 1 over mu naught. Now what we will do is we will just look at one single period in time domain and frequency domain. So it means I am just going to look from here to here. So that is one period in time domain. So of course period is given by 1 over mu naught. I am also going to look at one period in the frequency domain. This period is given by 1 over T max. Okay. So that essentially is a Fourier transform pair. Okay, and that in essence is what the discrete Fourier transform is about. That we just look at one period in the time domain, one period in the frequency domain. So this means even though you are just dealing with one discrete data set which consists of a finite number of samples, the underlying meaning is that you are looking at one period of a periodic signal. Okay, this is something which you will not appreciate otherwise. The hidden meaning is that this is an infinite periodic signal for which one period you are looking at, and that is this n number of samples. And when I take the discrete Fourier transform, again it means I have an infinite number of frequencies, but out of that one period, that is what you will get as the calculations from a discrete Fourier transform. So this is in essence what a discrete Fourier transform is. So what I will do now is I will move from my framework here into the formulation of the discrete Fourier transform. So let's look at it mathematically a little bit more formally. So the sample rate, let us assume that this is exactly the Nyquist rate, which is 1 over 2b. So the total number of non-zero samples is then T max multiplied by 2b, and that I am defining it to be n. Okay. So this is the sampling rate. So total number of signals, so remember the signal exists only for T max. So the number of samples is this divided by 1 over 2b, which is multiplied by 2b. So I can write my sampled signal. So remember what I said, the first step that you do is sample the signal in time domain. So a sampled signal is just given by x of Tn, where Tn is n by 2b, multiplied by delta of T minus Tn. So this is my sampled signal in time domain. Okay. And so I can write its Fourier transform. So the Fourier transform of the sampled signal in the time domain is just this x of Tn multiplied by e to the power minus I prime Tn. Okay, so this of course is a continuous signal in frequency domain. Now what I am going to do is I am also going to sample it in Fourier space. Okay, so since the signal is limited in time from 0 to T max, the sampling rate in the frequency domain must be 1 over T max so that you have no aliasing. So your sampling frequency must be exactly 1 over T max. So the number of non-zero frequency samples, so remember your total frequency is twice 2b. So 2b divided by mu naught, so 2b multiplied by, so given mu naught is equal to 1 over T max, this translates to T max multiplied by 2b, which is exactly same as n. So therefore you have n non-zero signals in the time domain, you also have capital N non-zero signals in the frequency domain. Okay, so therefore when I sample the signal in the frequency domain, I can write that as xp of mu m is equal to summation equal to 0 to capital N minus 1 e to the power minus I 2 pi mu m multiplied by Tn, where mu m is n by T max. Okay, so this is just sampling in frequency domain. So I put everything together. So substitute Tn is n by 2b, mu m is n by T max, and I use T max multiplied by 2b is just equal to capital N. Then what I get is my sampled version, so one period of sampled signal in the frequency domain is given by an expression which looks like this. And write out in more general form, so just skip this mu m and Tn, x of n, x of n. Okay, so this is what you will normally see in all textbooks, that you will just get a simple expression, you get n number of samples, where n goes from 0 to n minus 1 of summation of x over n multiplied by this term here is giving you a discrete Fourier transform. Okay, so you have your DFT and inverse discrete Fourier transform. But just keep in mind the underlying principle. What is happening is, this is a sample version of the signal in the time domain. And so the signal is, it has n samples. In the Fourier transform, you will get infinite copies of that signal. You are also sampling the Fourier signal at this frequency k, given by this expression here. So you are making the signal periodic in the time domain. So your x of n, where n is from 0 to capital M minus 1, is just one period of a periodic time domain signal. And the same way, your capital X of k is one period of a periodic signal in the frequency domain. Again, k going from 0 to capital M minus 1. That is the true meaning of the discrete Fourier transform. So the DFT by itself has no information about time or frequency resolution. You just get a set of n numbers. So you don't know what the sampling frequency is, you don't know what the temporal frequency is either. So in order to get that information, you need to know some extra information about how the signal was transformed. It is DFT is just a transformation relationship between two sets of complex numbers, each of length capital N. So what you need to know is what is either the sampling interval or sampling in the frequency domain. One of the information you need to know. So if I know that my sampling interval in the time domain is delta t, then I know the total extent of the signal in the time domain is capital N multiplied delta t, and that is your t max. Then I can immediately work out what is my frequency resolution as well as my time resolution. So the frequency resolution is 1 over t max, which is 1 over capital into delta t. Okay, so some extra information needs to be provided in order for you to link the